magnets on Modern Marvels. For centuries, scientists have attempted to solve one of the animal kingdom's most perplexing mysteries. How do some species regularly navigate vast distances across the globe without getting lost? Recent studies suggest an intriguing solution to the puzzle. Researchers believe some animals use tiny natural magnets in their bodies that enable them to sense the Earth's magnetic field.
There is some evidence that birds and animals and fish use the magnetic field lines of the Earth to help them in their migration. They can find their direction, much like we do with a compass.
Just as animals may use magnets to survive in nature, we use them to sustain ourselves in a world of mechanization. Our enduring relationship with magnetism dates back to antiquity. About 2,000 years ago, the ancient Greeks and the ancient Chinese independently discovered Earth's only magnet crafted by nature. It became known as the lodestone, or magnetite.
It's an oxide of iron, and the basic properties of the lodestone come from its atomic structure, but how it's magnetized is still a bit of a mystery. We think there was lightning strikes hitting the rock and the magnetic fields from the lightning magnetizing the rocks.
Chinese innovators used the unusual mineral as part of a device made of polished brass. On its surface, a spoon-shaped lodestone was free to rotate in response to the Earth's magnetic field. It marked man's earliest step toward the first practical application of magnets, the compass. A compass's magnetic needle determines direction by aligning itself with the Earth's magnetic north and south poles.
If I place this in a little cup and allow it to float on some water so it's free to rotate, the compass will turn around and align itself pointing at the South Pole. If I reverse the magnet, the compass senses that the pole has changed and points the other way. Reverse it again, it swings back around.
By the 13th century A.D., the compass changed the face of sea travel, relieving sailors from plotting their courses solely by the sun and stars. When storms obscured the skies, they could still ably navigate. In the centuries to come, the curious began to slowly unravel magnetism's mysteries. William Gilbert, physician to England's Queen Elizabeth I, led the way in 1600 with his landmark treatise, De Magnete. It was Gilbert who first concluded that the Earth was indeed a giant magnet. More than 2 centuries passed before an accidental discovery produced the next crucial breakthrough. In 1820, Danish physicist Hans Christian Ørsted stumbled upon magnetism's inextricable relationship to electricity.
Hans Christian Ørsted was the first to demonstrate that electric current down a wire would produce a magnetic field. He just had a compass needle near a wire. When the current went on, the compass needle turned. When the current went off, the compass needle turned back.
And he thought this was very curious. This discovery tied together 2 separate disciplines, electricity and magnetism. Ørsted discovered that they're really one and the same thing.
A decade after Ørsted discovered that electricity creates magnetism, English scientist Michael Faraday demonstrated the reverse, that magnetism can produce electricity. He found that moving a magnet near a stationary coil of wire, or moving a coil of wire within a magnetic field, induced electric current.
The oscilloscope is connected to the coil, and it reads the voltage that is induced in the coil. So you can see as I move the coil through the magnet, the spot moves up and down in response. The faster you go, the greater the voltage. So if you need more electricity, you have to move it faster.
Faraday's discovery was monumental. It paved the way for the invention of the electric generator which enabled man to create electricity on a scale never before imaginable. The key to generating the power was to harness some form of mechanical energy in order to put the magnets or electric coils into motion.
In a hydroelectric plant, it's water falling over the dam through the sluiceway and turning the water wheel. In a coal-burning power plant, the coal makes steam and the steam turbine turns the generator. A wind power generator, the wind turns the blades of the generator. So the process is the same. Mechanical energy converted to electricity.
In the early 20th century, magnets were also empowering the reverse of this process, driving electrical motors that converted electricity to mechanical energy. The motors had eclipsed steam engines as the era's prime movers, propelling everything from trolleys to cranes to elevators. In a common electric motor, an electromagnet called the armature revolves between the north and south poles of a stationary magnet called the stator. The armature rotates until its north pole is opposite the south pole of the stator. The direction of the armature's current is then reversed by a device called a commutator, changing its north pole to a south pole. The two south poles repel each other, pushing the armature forward. The current reverses every half turn, keeping the armature in motion by frustrating its effort to bring north poles near south poles. Magnet-driven motors and generators accelerated the 20th century's modernization through electricity. Two inextricably linked industries powered one another's advancement.
The rise of the electrical industry involved a great growth in the use of magnets. And also these things worked together. As the industry grew, magnets got better. As magnets got better, the industry grew. So it was very much a symbiotic relationship between magnets and electricity.
Experts advanced both industries by developing new generations of magnets with ever-improving properties. The first commercial magnets were made from carbon steel and later tungsten steel. These were stronger than the naturally occurring lodestone, but heat and jarring could significantly reduce their magnetism. In the 1930s, researchers created a stronger, more heat-resistant variety called Alnico, an iron-based alloy containing aluminum, nickel, and cobalt. Still widely produced today, they stored greater magnetism in a smaller package. But without an electric jolt, their magnetic potential remained dormant.
You need a very large magnetic field to magnetize them adequately. So what you want to do is have an electromagnet with a large current.
Magnetizing the material is a swift and simple process. Just place the wannabe magnets close to an electromagnet, then turn on the juice. The intense magnetic field realigns the alloy's atoms to make it magnetic. In the 1950s, Alnico magnets were joined by low-cost compact alternatives called ferrites. Today, these iron oxide compounds account for about 90% of the permanent magnet market.
The ferrite magnets allowed motors to be made in a smaller diameter, shorter length, and really the application fitted itself very well for the automobile industry. Now you could have seat positioner motors, for example, that fit very nicely beneath the passenger seat, and window lift motors that were now small enough to fit very nicely into the door of an automobile.
Today, magnets play a key role in not only our cars, but also our computers. Researchers exploring new frontiers in that field are beginning to see the light. The most powerful known magnetic object in the universe is a neutron star, SGR 180620, in the constellation of Sagittarius. Its magnetic field is 1,000 trillion times stronger than Earth's. Magnets will return on Modern Marvels.